Hello everybody, welcome. This is paper 1 from May 2024 and this is time zone 2. Let's have a look and see what we can do. Alright, question 1 starts off with a statistics question. Let's have a read. The prices in dollars of 10 different garden chairs are 79, 139, 255, and then they list the rest of the 10 chairs. The first question asks us to find the range of the prices of the 10 chairs. Alright, so it's a 2-mark question. We're going to need to show some process. The range formula isn't given to us in the formula booklet, but the range is just the distance from the max to the min. So the distance between the highest and the lowest price chair in this case. So for A, let's write this out. Range itself is equal to the maximum minus the minimum. And in this case, the maximum value is 255, and the minimum value, the smallest one, is 49. And the difference between would be $206. All right, nice way to start off, I suppose. Second question, they're asking us to use your graphic display calculator to find the mean price of the chairs, that is to say the average price, and the next one is the standard deviation. Alright, so let's go and start with B1. Okay, so we're going to need to go to the calculator screen for this. Let's do that now. Let's go into spreadsheets, set up a column, and enter the values. In this case, it's just one variable, just the prices. So 7, 139, 255, and so on. 229 and 49. I think it's always a good idea, or at least a decent idea, to check through the values just to make sure that everything is correct. Okay, looks good. Alright, so we need to find the mean and standard deviation. Let's go and run a statistical test. Menu, statistics, stat calculation. We're just dealing with the prices of these chairs, so it's going to be one variable, statistics. Alright, and then where did we enter the data? In this column we called X. Alright, let's find the mean. Let's scroll up, and here it is. Mean is given by X bar. So in this case, the average price of the chairs is $137.10. So let's go back to the document and write that out. So B1 X bar is equal to $137.1. Alright, let's go back to the calculator and find the standard deviation of the price of the chairs. Standard deviation, this question is actually a little more complicated. We have this Sx, which is the sample standard deviation, and then this sigma x, which is our population standard deviation. So let's just go back to the document for a sec, because we see we have these two different values here on the calculator, but let's go back to the document and kind of talk about this. So in this case we have 10 different garden chairs, and we're not using these values to say something more generally about, let's say, the prices of garden chairs, I don't know, across the state or the province, or the prices of garden chairs in a catalog, and we've just chosen a sample. These are the 10 garden chairs that we want to know something about. In this case, we want to know the standard deviation of these 10 garden chairs. And this is the population. This is all of the garden chairs that we are interested in knowing something about. So in this case, we would choose, going back to the calculator for a sec, we would choose the population standard deviation because these are all of the chairs under consideration. If we just had a sample, let's say we had these 10 garden chairs and there were really, like, I don't know, maybe 100 different chairs in a catalog, and we wanted to find the standard deviation of the prices of all the chairs, and we didn't look at all the chairs, we just grabbed a sample of 10. In that case, based on this result, we would choose the sample because we just have part of a larger population. But since these 10 chairs are the only chairs that we're really interested in, and we want to know the standard deviation of these 10 chairs, and these are all the chairs we have, and this would be the population. So let's go back to the document here, and let's write in the population standard deviation. So let's go B2 standard deviation, which is 74.1 4, 6, 9, 4, or let's round this to 3 significant figures, 74.5. Good. All right, let's go on. In a sale, the price of each of the 10 garden chairs is reduced by $20. C is asking us to write down, and the first part is the new mean. So write down the new mean. So C, oops, here we are. C1, the new mean. So the mean is essentially the average. And our old average right here was 137.1, or let's even do this, 10 cents, I guess. $137.10. If every single chair is reduced by $20, then the average price of the chair would also be $20 lower, because everything is consistently reduced by $20. If we were to add these up again, then the mean, the new average, would itself be $20. So let's go ahead, and I'm going to write this out as x bar n for new. And this is 137.10 minus $20. So our new average would be 117.10. For part 2, this one's a little more challenging. The new standard deviation, I guess it's a conceptual question. I'm going to draw a little diagram, and hopefully this will explain things. So, not necessarily for these 10 garden chairs, but if we go out into a large enough population and we're looking at, let's say, the prices of chairs or the heights of individuals or something like that, not always, but oftentimes we'll have something like this standard normal curve, and I'm sure you've seen this before. And this standard normal curve is symmetrical. Here's the mean, and then we also have the standard deviation. Actually, I'm going to use the same color. Then we have the standard deviation, which talks about how spread out these values are. And if every chair is itself reduced by $20, so what are we doing? Well, we're actually just shifting this whole curve down by 20. And that helps explain why, for example, the new mean, so I should put this little bar above. The new mean is itself 20 lower, because every single value was shifted by 20. But if we look at the standard deviation, which is a value which discusses the distribution, or how spread out the values are from one another, the values are still relative to one another, spread out by, well, not roughly, but the exact same amount. That is to say, if this value right here is reduced by 20 and this is reduced by 20, the relative spacing between these values remains the same. And so the standard deviation, which is a measure of spread, the values are still spread out in the same way as they were originally. So rather than needing to put in all of these values back into our calculator and find the new mean and the new standard deviation, if they're all reduced by 20, the average reduces by 20. And the standard deviation, which is a measure of how spread apart these values are relative to one another, that doesn't change because they're all reduced by 20 consistently. So in this case, the standard deviation would stay the same. So let's write that in. Standard deviation, we don't need to put this n, but I'm going to. Standard deviation, the new one, is going to be, well, the same as the old one in this case. It's going to be 74.5. That's how spread out the values are from one another, and that hasn't really changed. Okay, let's go on. Part 2, we have a trigonometry question. Here we go. The diagram shows a toy crane. Let's read this question. They tell us that AB is equal to 25, AC is equal to 15, and then BAC is equal to 22 degrees. The first question, they're asking us to calculate BC, and it's a 3-mark question, so we're going to need to show some process. So we're in the realm of non-right angle trigonometry, because this right here is definitely not a right angle. Neither is this, and neither is this. It's not indicated. So for non-right angle trigonometry, we have the cosine rule, the sine rule, and then the area formula. The sine rule, remember, requires an angle and its opposite side length, and then we're going to need another pair of an angle and its opposite side length. So they're asking us here, they're asking us to find BC, for example. BC, I'm actually just going to draw that here. I'll give it blue, I suppose. So they're asking us to find this side length BC. And the question is, well, what can we use? Can we use the sine rule or the cosine rule? The sine rule is always the easiest, so it's not a bad way to first check out if we can use the sine rule. So angle, opposite side length, and then we see we don't have any other angles. We just have this one angle here. So we're not going to be able to compare this with an angle side length pair that we already know. In that case, we're going to need to use the cosine rule. Let's ask if the cosine rule will hold up. The cosine rule, remember, requires let's use this color here, 1, 2, 3 side lengths, and then a corresponding angle. And in this case, we do have all of these things. We have 1, 2, 3 side lengths, 1, 2, 3 side lengths, and a corresponding angle. So in this case, we have everything that we need to use the cosine formula. I'm just going to show you just as well a strategy that you can potentially use is if you've narrowed it down and you've asked yourself, okay, well, it's definitely a non-right angle triangle. What does my formula book have? Well, we have the sine, cosine, and the area formula. In this case, here we have side length. Oops, let me use this. So side length, opposite angle, side length, opposite angle. This is 1, 2, 3 side lengths, and then the corresponding angle. So remember, as you go through it, these two correspond to one another. So whatever is all by itself, this one is the angle that corresponds. All right, so let's go ahead and let's go back to the document. Okay, so let's go ahead and write out the formula or the formula for our cosine rule. It's a squared equals b squared plus c squared, which is actually a lot like the Pythagorean theorem, but then we need to adjust because it's a non-right angle triangle. BC cos A, and remember these two things pair with one another. So this side length, this one we're trying to find, must pair with this 22 degrees. We can't just put in the 22 or 15 in any which way we want. So let's go and substitute those values. So x squared, we don't yet know. X squared is equal to b squared plus c squared. These actually, it doesn't really matter the order. B squared plus c squared minus 2bc cos, and we do know that this is 22 degrees. Okay, so that should be part of our process. Remember, we do want to include a fair bit of process, or enough for our 3 marks here, or that they're expecting for 3 marks. Let's go to the calculator and work this out. Here we are. Let's go into the calculator screen. One thing you want to be mindful of, make sure this is in degrees. When we're doing AISL, we never need radians. So if it says rad, R-A-D, change out, need to be in 2 degrees. Okay, I'm actually going to, there's 2 different things. We could end solve this, or, actually, you know what, to be honest, I am actually going to end solve this. So let's put our equation in. Menu, algebra, numerical solve, and let's put our equation. We have x squared is equal to 15 squared plus 25 squared, sorry about that, minus 2 times 15 times 25 times, let's get cos 22 here, that's funny. Math expression available in menus in the catalog. I don't know what that means. Cos 22. Okay. Make sure this is good. 15 squared plus 25 minus 2, 15, 25 cos 22. And let's ask the calculator to solve for x. There we are. So here we are. It's 12.4343. So that's the length of this side length. Let's go back to the document and write that in. X is equal to 12.4343, or to 3 sig figs, 12.4, I suppose. And in this case, just for good measure, we can put our units 12.4 centimeters. All right, given that ABC is acute, calculate angle ABC. So first off, let's maybe clear some space. There we go. So what are they asking when they're asking for this ABC? Easiest way to do it is look where the top hat is. That's angle B is what we're looking for. Another way is to trace it out, and it's always the middle one, ABC. So we're looking for BC. An equivalent way that these are sometimes written is like this, ABC, and then it's again always that middle one here. So what are we looking for? We're looking for this theta value here, angle ABC. Let me just indicate that A. And then let's find B. I'm going to try to write it in here just so you can still see this diagram. So ABC is acute. We just found this 12.4 centimeters. So I'm actually going to write that in because it may be useful for us. So remember we said that cosine rule, or sorry, the sine rule is always the easiest one to apply, the more straightforward I think it is. And the cosine rule, well, the cosine rule, if we need to, we can use it as well. In this case, we can actually use both, but again, the cosine rule might be a little more involved. So let's ask if we can use the sine rule here. So angle opposite side length, and if we have another angle opposite side length pairing, then we should be able to use the cosine rule, and we do. So let's go ahead and use our sine rule. Sorry, our sine rule. Now we can use. So we have, what do we have? We have B over sine B is equal to, and in this case, what other pairing do we have? We have A over sine A. I know in the formula booklet it has equals C. It has like a chain of equivalences. You really only need a pair. So let's go ahead and put those values in. In this case, we want to find, whoops, sorry, I messed that up. I messed that up pretty bad. Let's go ahead and just change those values. B over sine B, that looks a little better. I thought it looked a little funny. Over sine A. There we are. Okay. So B is 15 over sine theta is equal to A. A is equal to 12.4 over sine 22. Now we might have wanted to put the sine at the top and just rearrange this, but with nsolve, to be honest, it doesn't actually matter all that much. So let's go ahead and go back to the calculator and work this out. All right, let's put these values in. Menu, algebra, numerical solve. Oops. Here we are. Menu, algebra, numerical solve. 15 over sine, let's just call it x. That should be fine. Oops. Sine x is equal to, and this is going to be another fraction, 12.4 over sine 22. Sine 22, and then let's ask the calculator to solve for x. Make sure we're in degrees. Still good. So the answer in the end is 26.946. Let's go back to the document for a sec. Therefore, we know that theta, or what could we say? Yeah, let's say theta. Theta is equal to 26.9462, or theta is equal to 26.9236 figs. And then let's put our degrees. So what I was saying actually initially, and these are equivalent, is we could have written this as sine B over B is equal to sine A over A. And this would have been an equivalent form, and I believe it's even given to us like that in the formula booklet, but nsolve will take care of the algebraic manipulation for us, so it's okay either way. Okay, not bad. Let's keep going on. Question 3. 5-mark question, so it should be a fairly quick question. Sunita sorts 300 peppers into sizes of small, medium, or large. Some peppers are red, some are green, and some are yellow. The following table shows her results. Okay, so we've got the small, medium, large peppers, we've got the red, green, and yellow peppers, and we've got, I guess, this table which compares these two variables. Sunita wants to test at the 5% significance level whether the size of the peppers is independent of colors. State the null and alternative hypotheses for this test. So we're in the realm of hypothesis testing. What do we have? We either have, our chi-squared independence test, the goodness of fit, or the t-test. This definitely isn't the goodness of fit. There's not just two columns, so we're not just comparing the means or the averages, which would be a t-test. Here, I guess the one big kind of hint is it's independent. We want this 5% significance level, and when we want to see if one of these variables is independent of the other, or sorry, these two variables are independent of one another. In this case, the color is independent of the size, or is it not? So let's go ahead and go through part A. So we're in this chi-squared independence test. Part A asks us to state the null and alternative hypotheses. For independence, chi-squared independence tests will always have blank, let's go null hypothesis, an alternative hypothesis. The null hypothesis is always going to be blank, is independent of blank, of one other variable. Remember, null is kind of like, since 0, this is the status quo in some sense. There's no relationship between these two variables. And then the alternative is blank is not independent of blank, the other variable. It's always going to have this structure. And in this case, we would say that, well, Sunita wants to test whether the size of the pepper is independent of color. And so the null, the kind of 0 case, null like the German null, the 0 case is that size is, we could say size of pepper, but size is independent of color. I'm going to write this here, size of pepper. Do we need to? I'm not sure. To be honest, I always think it's better to err on the side of caution in some ways. Size of pepper is not independent of color. Let me just clean that up. Is not independent of color of pepper. Just because, yeah, err on the side of caution, I suppose. Size of pepper is independent of color, or it's not. That is to say, there seems to be some kind of interaction between these two variables. The critical value of the test is 9.49, and then they're asking us to find the chi-squared value, that is to say, calculate the chi-squared value, and then the conclusion of the test, and give a reason. Alright, so they gave us this. They gave us the chi-squared critical value of 9.49, which is our cutoff point. And we also know this 5% significance level. Let's go run a chi-squared test, and then we'll see what the results give us. So let's head back to the calculator here. Alright, let's go to our calculator. Let's go Menu, Matrix. We're going to create a matrix. Alright, and if we look at this, there's no totals or anything like that. It's a 3x3 matrix. So there are 3 rows, and there are 3 columns. Alright, let's put those values in. 18, 31, 46. I'm just going to enter those here. Oops. Just going to give a quick check to make sure it's all good. And it looks like it is. Alright, now we need to define our matrix. And let's do that by using this control var. So control var, this arrow we want. And you can call your matrix whatever. I'm going to call it A. Alright, let's make sure it's defined. When you press A, there's our matrix. Okay, let's run our stat calculations now, or our stat test rather. So let's go into statistics and look at our stat tests. In this case, we want to run a chi-squared two-way test. This isn't the goodness of fit, it's a two-way test. The matrix, we defined it as A. And let's go read off our values. Okay, So here we have degrees of freedom, we have the chi-squared value that we found, and we also have a p-value. So either of these will be enough for us to determine whether we should accept or fail to reject the null hypothesis, or reject the null hypothesis. So let's go back to the document for a sec and look at what we have here. Okay, so state the conclusion of a test. Give a reason for your answer. So the p-value itself was given by 5%, and our p-value, so I'm actually just going to write this out. I hope this isn't going to be too long. P-value is 5%, or let's write this out as 5%, or if we wanted to, 0.05, right? And the p-critical value, that is to say the one that we found, oops, let me just rearrange this real quick. P-critical value, and since our significance level is 5%, and the p-value that we found was 0.000156, or yeah, let's write it as that, 0.000156. And for our chi-squared critical value, it was 9.49, and our chi-squared value itself that we found was equal to 22.55, roughly speaking. Okay, so what do we want to do? Do we reject or accept the null hypothesis? There's two different measures we can use, and they're both equal to one another. So looking at this value right here with a p-value, we see we have a 5% significance level, and this 5% significance level is in some sense our arbitrary cutoff point. It's the level of assurance that we would need to either accept or reject the null hypothesis. So in this case, our p-value, that is to say the probability in some sense that the null hypothesis is true, is super, super small. Like the chance of us seeing these kind of results, the relationship between this small, medium, large, and red, green, yellow pepper, seeing this kind of relationship right here in this table, the chance that we see this just based on probability and similar proportions is 0.000156. Super small chance we see this kind of relationship just based on probability and proportions alone. So to what extent can we say that the size of pepper is independent of color? Well, no, actually. It seems that the chance of seeing these results is so unlikely that it gives us some reasonable kind of, what can we say, a certain level of certainty, I suppose, or some reasonable belief to reject the null hypothesis. So here we would say that, let's write it out, we would say the p-value is less than the critical value. That is to say 0.05, whoops, sorry, the other way around, 0.000156 is less than 0.05, and then what would we do? We would reject the null hypothesis. All right. So that would be one way to do it. The chi-squared critical value and the chi-squared value that we have here, the chi-squared value is a measure of the difference between observed and expected. So if there's a big difference between what we observe, let's say in this table, and what we would expect just based on chance alone, that is to say, like if a third of the peppers are large, we would expect, well, a third of the red peppers to also be large. Just based on similar proportions alone. If there's a big difference between what we observe and what we expect, then the chi-squared value will be very, very big. And that's exactly what the chi-squared value is, the difference between what we observe and what we expect. In this case, this is our cutoff point, 9.49. That's the amount of difference that we're willing to tolerate in some sense. And this is the amount of difference that we found. So we found that in this sense, our chi-squared value was greater than chi-squared critical value. In this case, 22.55, the amount of difference that we saw between observed and expected was much larger than the cutoff value, the kind of amount of difference that we were willing to accept. And so this also leads us to, in the same way, reject the null hypothesis. Either one of these would be fine. You don't need to put both. P-value, the probability that the null hypothesis is true. The probability that we see these kind of results just based on chance alone. Super, super small. Sounds like there's something going on here. Very unlikely we see these results. Let's reject the idea that they're independent and not related. Chi-squared value, measure of difference between the observed and the expected. Large chi-square value tells us there's a big difference between what we observe and what we would expect just based on chance alone. Since there's so much of a difference, it seems like these variables are interacting with one another. Therefore, chi-squared value greater than chi-squared critical value, we reject the null hypothesis all the same. Alright, let's go on. Alright everyone, let's continue on with question 4. At a particular building site, the number of square meters of bricks N that can be laid in one working day varies directly with the number of bricklayers B. 5 bricklayers can lay an area of 60 square meters of bricks in one working day. Calculate the area that can be laid by 7 bricklayers in one working day. Alright, so I'm just going to draw a quick diagram to kind of show what's going on here. Maybe get a little more real estate, I guess. Here we go. So just drawing a quick little coordinate grid. If these are the number of bricklayers, and this is the number of square meters of bricks, what we're saying is that as we increase the number of bricklayers, we can also increase the number of, bricks that we're laying in terms of the square meters of bricks that we're laying. So what is the relationship? As we increase the number of bricks, we can increase the number of square meters of bricks that we have. And there's a few key words that I think narrow down and allow us to determine what type of question this is. And that would be this right here. This varies directly. So we're looking for often these two kind of keywords which tell us that we're in this realm of direct variation. And we'll often see these words like varies directly, sometimes varies directly with the square or varies directly with the cube, or we'll see that it is proportional. So it's something is proportional to, let's say, the square of or the cube of something. So once we're in this relationship of direct variation, we'll have this idea of y is proportional to x, or in this case, the number of, let's say, square meters of bricks is proportional to the bricklayers. And so the other key piece of information, once we've narrowed it down to this idea that we're in the realm of direct variation, is to see if it's, let's say, varies directly with the square or the cube of, let's say, some value. In that case, if we had some value, let's say, I don't know, the number of, or the amount of, I don't know, tools, this is a silly example maybe, number of tools or the amount of electronic devices or something like that, and the number of bricks, and we said that this was proportional to the square of tools we have, then we would have this square relationship. And again, it would pass right through the origin. In this case, it just varies directly, so we're going to have this linear rather than this quadratic relationship. But we're going to have this number of bricklayers is proportional to B. So let's go ahead and write that out. So the number of bricklayers is proportional to, the number of bricks that we can lay is proportional to the number of bricklayers. We want to find a constant that connects these two values. So the number of bricks that we can lay isn't just equal to the number of bricklayers. It's going to be multiplied by some constant. So if we have the number of bricklayers, multiply it by some constant, and that'll tell us the number of bricks that we can lay effectively. So how can we find this constant? Well, they tell us that 5 bricklayers can lay 60 meters squared of bricks. So we can lay 60 meters of bricks, 60 meters squared of bricks, when we have 5 bricklayers. Now we can end solve this to find k, or we can just do a little bit of algebra, divide both sides by 5, so 60 divided by 5, k is going to be equal 12. So calculate the area that can be laid by 7 bricklayers. We know we have this equation where n is equal to k times b. The number of square meters of bricks we can lay is equal to, we found k was equal to 12, so 12b. Effectively, that essentially means that for each bricklayer, we can lay 12 more bricks in one working day, or sorry, 12 square meters of bricks in one working day. So if we have 7 bricklayers, n is equal to 12 times 7. In this case, we can lay 84 meters squared of bricks. So just to review that once again, because I think there's maybe potentially a lot going on here. They told us that the number of square meters of bricks is proportional to the number of bricklayers. More bricklayers, more bricks that we can lay. But the number of bricks that we can lay isn't just equal to the number of bricklayers, it's multiplied by some constant. And the question is, okay, well, what is that constant? Thankfully, they give us a set of, essentially a coordinate point. They tell us that when we have 5 bricklayers, we can lay 60 square meters of bricks. And this will tell us that, okay, what is that constant that we're going to need to make that true? And this tells us that, okay, well, 12 is the proportionality constant in this case, or in real world terms, that for every additional bricklayer, we can lay 12 more square meters of bricks. So if we have 7 bricklayers, 7 times 12 gives us this 84 square meters. Okay, let's go on to part B. So direct and inverse variation is something that's been coming up a little more frequently on more recent exams. So maybe something to potentially be mindful of, but it also means that, yeah, maybe it's going to be something new on the next one, so you never really know. All right, next question. At another building site, the time t, hours, it takes to lay bricks varies inversely with the number of bricklayers. So it varies inversely with the number of bricklayers. And that should make sense as well. If we have more people working a job, it's going to take less time to complete. So just like in this original question, we saw the varies directly, and we knew that as one thing was increasing, the other one was increasing as well. As one thing was increasing, the other thing was increasing as well. For varies inversely, it's going to be the opposite relationship. I'm going to draw a little diagram down here to show you. So for varies inversely, we can have this y is proportional to, and maybe some of you are thinking, okay, inverse is yes, 1 over x. And we're going to have this relationship as well. One increases, the other variable actually decreases. So this would be y is inversely related with x. And then just like the last example as well, there's nothing to say that it can just vary inversely. For example, we can have y is inversely related to the square of x, or the cube of x, on more challenging questions. And all that means is that it just gets a little steeper. All right. So here they told us that the time it takes varies inversely with the bricklayers b. So time is proportional to, but inversely proportional to, the inverse of the number of bricklayers. In this case, time just doesn't decrease with the number of bricklayers in a kind of straightforward fashion. The time won't just simply be, let's say, halved in, what can we say? It won't simply just be equal to 1 over the number of bricklayers. How long does it take to complete if there's just 1 bricklayer, 2 bricklayers, 3 bricklayers? For this, we need to find, once again, a proportionality constant. So time is equal to, well, some initial value, and then divided by the number of bricklayers. Again, they give us a value. They tell us that 5 bricklayers take 8 hours to lay an area of 60 meters cubed. In this case, we want B is equal to 5, just like we have here. That's a little loud. B is equal to 5, and T is the other value right here. And there we go. This is kind of like what is it called? Like a red herring, something like that. We don't actually need the number of bricks for this formula. So let's go ahead and put in those values. T is equal to 8, K is what we want to find, and B is equal to 5. Once again, we can end solve this if we want, or just do a little algebra here, and K is equal to 40. So we found what we needed for this constant to complete our equation. So I'm going to actually just rewrite it up here. That means that T is equal to 40 over B, because we solved for K. So what does this mean effectively, I suppose? That if we have one bricklayer, it takes 40 hours, I suppose. If we have two bricklayers, it takes 20 hours, and we have this 40 initial value, and we keep dividing by B as B gets larger. The time itself will decrease. So if we wanted to change this, this is the number of bricklayers, this is time to complete the job. It gets lower and lower and lower. So let's calculate how long it takes for 12 bricklayers to lay an area of 60 meters cubed. So T is equal to 40 over 12. So 40 divided by 12. I guess we can simplify this. What is this going to be? Divide both the top and the bottom by 4. T is equal to 10 over 3. Do they ask us? They don't actually ask us to write it in minutes or hours, so I believe this actually would be okay. 40 over 12, 10 over 3. If you wanted to, I'm sure you could write it as 3.3333 hours. That would be okay. If we wanted to be very kind of specific, we could say 3 hours and 20 minutes, I guess. A third of an hour. Alright. I think that's it. Calculate how long it takes 12 bricklayers to lay an area of 60 meters. Proportionality constant of K, 40. 12 bricklayers, solve for T. And I think we're good. Alright, let's keep going. Alright. Financial mathematics, 9-mark question. Let's see what we can do. So sometimes when you see a financial mathematics question, it can kind of be a relief because sometimes they're actually kind of straightforward. Sometimes they can kind of be unnerving, but let's see. Imani invests $3,000 in a bank that pays a nominal annual interest rate of 1.25% compounded monthly. So we've got $3,000 annual interest rate of 1.25, and it's compounded monthly. Okay, that's all key information. Calculate the amount of money Imani will have in the bank at the end of 6 years. Give your answer to 2 decimal places. Okay. So we have someone, they're taking a certain amount of money, they're putting it in the bank is paying out interest at a monthly rate, and we need to, or we're asked to find how much money we'll have at the end of a certain amount of time. So this is a straightforward kind of compound interest problem. There's 2 different ways. We can either use the compound interest formula or the financial solver. I just want to show you, going to the formula booklet, here is our, actually let's go look. This would be under, I believe it is right here, yeah, number and algebra. This is our compound interest formula, and they even tell us what each of these values are, present value, K and R. I think for these kind of questions, compound interest formula is potentially, it looks complex, but I think it's more straightforward in comparison to the financial solver, just because there's more ways to err when you use the financial solver. So I'm going to use the compound interest formula, and I'll show you how to do it with the financial solver as well. Alright, let's go with A. So our formula is the final value is equal to the present value 1 plus r, the interest rate, 100 times k, compounding period, number of years, and then k, number of times it's compounded per year. So the final value is what we want to find out. The present value, we're putting $3,000 in the account. 1 plus the interest rate is 1.25%, 1.25, and the number of times it is compounded is 12 times a year. Again, number of years is 6 years, and number of times it's compounded is 12. So that's it. I'm going to go to the calculator screen and type this out. So here's 3,000, 1 plus, this is the interest rate, 100 times 12 over here, and this is going to be 6 times 12. And we have 3,233.53. Let's just make sure that's all okay. It looks like it is. All right. So I'm going to go back to the document here. Final value is equal to 3,233.53. And they're asking us for 2 decimal places, so it already looks like it's fine as it is. Okay. If you want to see how this would work with the financial solver, this is how it would work. Again, I wouldn't necessarily recommend this, just because I think there's more ways to mess up in some ways, I guess. All right, anyways, interest rate, they told us, is 1.25. The present value of our investment is 3,000. General convention, money flowing out, money flowing in, money flowing out, leaving our pockets, going into the bank, it's negative 3,000. Payments, 0. There's 0 recurring payments. We're not adding anything new. And the bank isn't, let's say, paying us installments as a pension or anything like that. Payment is equal to 0. Final value is what we want to know. Payments per year. In this case, for a simple compound interest problem, CPY and PPY we would keep the same. So compounding periods per year, the bank gives us interest 12 times a year. For compound interest, basic problems, we keep these the exact same. It's just going to be a lot easier in terms of calculating the total number of payments. Total number of payments is connected with PPY, and in this case the bank gives us interest 12 times a year because it's compounded 12 times a year. So the total number of payments, 6 times 12, 12 payments for 6 years, 72 payments. Final value is again 3,223.53. That's our final value. I think that's more involved, but if you're strong with the financial solver, then of course it's another way to work it out. Okay, let's go on to the second part, part B. Here we go. Going back to the document. Calculate the number of months it takes until Amani has at least $3,550 in the bank. I'm going to use this compound interest formula once again. So, final value, she wants $3,550 in the bank. The present value is equal to 3,000. We have our interest rate of 1.25, and again, it's being compounded 12 times a year. N is what we don't know. We don't actually know what N is, but we know it's compounded at 12 times a year. After that, it's just a matter of, I'm going to actually erase this because we can just, from this point onwards, and solve. And solve for N in this case. And that would be it. That would allow us to find this value. Can we do that? Let's go back to the calculator. I'm actually going to, I think I'm going to work it out on the financial solver, because there's our formula, and I'll work it out on the financial solver as well. And we just need to do it once, really. So let's go financial solver. I guess one thing is it's nice it's set up for us again. So in this case, we don't know how long it'll take. Interest rate is still 1.25. Present value is 3,000. Payments is 0. The final value, she wants to have 3,550 in the account. Payments per year, 12. So I guess everything's set up for us nicely. Let's see the amount of time it would take. 161.68. So 161.686 months. Let's go back to the document. Here we are. So n is equal to 161 what can we say, 69 months. In some questions it matters. In this question, I looked at the formula earlier and it looks like they are accepting the decimal, but again, if they're asking us for the number of months, the bank pays out interest at the end of the month. So in this case, after 161 months, we don't yet have $3,550. After, what is it, roughly 0.7, so maybe like, what can we say, 22 days in the month, we have it, but the bank hasn't paid us interest yet. It's not until the 162nd month that we have the total amount that we want in the account. So I think that's a better answer, actually. 162 months. All right. Let's go on. Amani uses the $3,550 as a partial payment for a used car costing $22,000. For the remainder, she takes out a loan from the bank. Write down the amount of money that Amani takes out as a loan. Okay, so part C. So here, she wants to buy a car for $22,000. The bank often will require some initial kind of down payment, and in this case, she is paying $3,550. Car costs $22,000. She's giving the bank $3,550. So how much does she need to actually borrow from the bank? Well, $22,000 for the car, but she's already paid off $3,550. So what is the size of the loan? I'm actually going to work that out on the calculator that I have beside me here. And that would mean the size of the loan would be only $18,450. Okay. Let's go on. The loan is for 8 years, and the nominal annual interest rate is 12.6%, and again, it's compounded monthly. So the loan is for 8 years. Imani will pay the loan in fixed monthly installments, so she'll pay back every single month at the end of each month. Okay. Calculate the amount correct to the nearest dollar that Imani will have to pay the bank each month. All right, so here we are in the realm where we're going to need to use the financial solver. All right, so got a lot of information here. Let's go to our financial solver. Here it is. I'm actually going to erase this information and we're going to need to start again. Okay, so interest rate I think is always the easiest one to start with. 12.6%. The present value, what's the size of the loan that she took out? $18,450. General convention, money flowing out, money flowing in. She's got $18,450 that came her way to buy this car. So $18,450. All right. The payments, we want to find out how much she has to pay. The final value of the loan, ideally, it goes to 0. Payments per year. She pays fixed monthly installments. That is to say, she pays at the end of every month. She pays 12 times a year. And CPY. CPY is the number of times the bank gives us interest, compounding periods per year. In this case, the bank compounds the interest that we need to pay 12 times a year. Payment is at the end. Everything looks good. The number of payments, well, remember we said PPY was related to N? So N is the total number of payments. So if it's 8 years, 8 years times 12 payments a year gives us 96 total payments. All right, everything looks good. And she must pay $305.98. So let's go back to the calculator, sorry, the document, and it's $305. Sorry, I should actually be clear in terms of the process that you would need. For a 3-mark question, it is not enough to just put 305. We would need to show our process, and that would look something like this: NI, PV, PMT, and so on. I don't know if I want to write this all again. PPY and CPY, and then put the values in for each. So in this case, 96, 12.6, make sure it's legible, of course, 18, 450, and so on. I'm not actually going to do that again because we kind of saw it earlier. So there's our method mark. And oftentimes, even if you're unsure, actually, one of the method marks is attempt to use financial solver. So writing this out and kind of giving it your best shot. Not consistently, not always, but often. There'll be a method mark for attempt to use a financial solver. So don't leave those process marks kind of just lying there, I suppose. So here it is. Here's our values. And then PMT is what we were trying to find. PMT is equal to 305.98. Remember, they asked us for the nearest dollar, so this would be 306. That's how much she needs to pay every single month. Okay. All right. I hope it's okay to leave this like this, but obviously not on an exam. Not on an exam. Final value, it's not too bad. There it is. Okay, let's go on. Halfway through. Here we go. Jerry makes handcrafted chocolates. On average, 1 in 25 of the chocolates that Jerry makes is flawed. Whether or not a chocolate is flawed is independent of all other chocolates. In a batch of 20 chocolates chosen at random, find the probability that 2 are flawed or more than 2 are flawed. Okay, so what kind of question is this? It sounds like a probability question, obviously. We're asked to find the probability that out of these 20 chocolates, 2 are flawed and so. But what kind of a probability question? Since we're taking 20 trials, we're definitely not going to be able to use a tree diagram that's going to go on 20 times, because it's going to look, to be honest, it's going to look pretty crazy already by the 3rd or 4th round, or the first 3rd or 4th branch. So what do we have here? We have a statement of probability right here that 1 in 25 of the chocolates that Jerry makes is flawed. We have a statement that the probability that 1 is flawed or another is flawed are independent. That is to say, if 1 is flawed, it doesn't influence the probability that the other is going to be flawed. And we have a set number of trials. And we have constant probability across trials. So 1 in 25 are flawed. We have 20 trials. The probability that 1 is flawed doesn't influence the probability that another, and it can either be flawed or not flawed. So we have this binary situation, flawed or not flawed as well. In this case, this is a binomial distribution, 20 trials, and then we have a consistent probability across trials. So after we find that it is binomial, that, to be honest, that narrows things down for us quite a bit. So a few different ways that we can write our process. The most conventional way is we say that x, some variable, can be approximated with a binomial distribution, and then we would say what is the number of trials and the probability that something is, in this case, flawed or not flawed. So in this case, we have our 20 trials, number of trials, and then the probability of something being flawed. In this case, it's 1 over 25. This is certainly acceptable, and this is maybe the more proper way. The IB will also accept calculator notation, and to be honest, I actually think that might be the easier way to go about it. So let's actually go to the calculator screen and see how we can potentially work this out. So here we are. Let's go into the calculator screen, menu, probability. In this case, we're dealing with a binomial distribution, and we can either use binomial PDF or CDF. PDF is just if we want to know if 1 is flawed, 2 is flawed, 3 are flawed. CDF is if we want to know whether there's between 1 and 3 or 5 or more are flawed, and that would be CDF. You can use CDF always, and to be honest, I hope this isn't too much of a tangent, but I kind of prefer CDF always because when it comes to normal PDF and normal CDF, they work in a different way. Normal PDF actually measures something different than the equivalent kind of binomial PDF. It doesn't measure a range of values up to a certain point or only those values. CDF, normal CDF is all we use, and you can kind of get into problems if you use normal PDF. So I almost kind of say, yeah, use CDF. And that's actually what I'm going to do here. So here we go. Number of trials. We have a batch of 20 chocolates. The probability of success, in this case, the chance of drawing a chocolate and it being flawed. And we know that's 1 out of 20. I'm not sure if the calculator will accept this. Will it 1 out of 20? 1 out of 20 is, at any rate, 0.04. I'm not sure if the calculator will accept fractions. In this case, we want to know the probability that 2 are flawed, and easy enough, we can just put the lower bound and upper bound as 2. And this would be our value. If we wanted to do it with PDF, we could certainly as well. To be honest, it might be more proper. 20 trials, probability of success, and then the x value is 2, and that would give us the same. To be honest, CDF I think simplifies it because it keeps things consistent across the norm CDF and binomial CDF. Okay, so there it is. Probability that 2 are flawed is 0.1458. Let's go back to the calculator. Sorry, the document. All right, here we are. So I'm actually going to write it out in the alternate way. You can also write this out. Binom. I'm going to write it out as CDF. Is 20, 0.04, 2, 2. And of course PDF is fine, but I just wanted to do this for consistency. And the answer is 0.146, I suppose. It's 3 sig figs. 0.146. All right. Let's go on and work through question 2. In this case, we want to find the probability that more than 2 are flawed. Be careful with binomial. In this case, it's more than 2. So when we're talking about the range of values, we can have 3 flawed, 4 flawed, 5 flawed, but we want more than 2. So 2 is not an acceptable value in this case. So going back to the calculator, let's go probability, distributions. Let's go binomial CDF, which we'll need to use this time. We're grabbing 20 chocolates. The probability that one of these is flawed is 0.04, or 1 out of 25. The lower bound needs to be more than 2, so potentially we can have between 3 and all the way up to 20 can be flawed. So what's the probability that between 3 and 20 are flawed? And in this case, it's 0.043863. So let's go back to the calculator, the document. Binom CDF. In this case, we can put in the calculator notation. 20 trials, probability of success, and then our range between 3 and 20. And in this case, the probability is 0.0439, and that's 3 sig figs. Okay, let's go on. Jerry sells the perfect chocolates for 50 pesos each and the flawed ones for 15 pesos. Okay, calculate the expected number of pesos Jerry makes from selling a batch of 20 randomly selected chocolates. Okay, so he's selling 20 chocolates, and he makes a little more money, or he sells rather. He makes more money on the perfect chocolates than he does on the flawed ones. So out of a batch of 20, how many would we expect to be perfect, and how many would we expect to be flawed? If you're unsure on something like this, on these kind of questions, or even any question really, I think often, especially if you have the time, it's not a bad idea to look at the formula booklet. So here we know we're in the realm of statistics and probability. So just looking down here, we can ask, what is it? And then maybe it's not so clear because it's called the mean or the average. But this essentially is EX, might kind of jog your memory. This is the expected value. The number of trials, in this case 20 chocolates, and the probability of occurrence. The probability that it will be flawed or not flawed. So that should potentially help. So let's go back and use that idea. So we know he makes $50 on every perfect chocolate. And if we've got, let's say, the number of perfect chocolates is equal to, well, the probability of a perfect chocolate, 1 in 25 are flawed, and that means that 24 out of 25, or roughly 96% of these 20 chocolates are going to be perfect. And the number of flawed chocolates, well, the chance that one is flawed we saw was 0.04, or 1 out of 25. And we would expect 1 out of 25 of the 20 chocolates to be flawed. So I'm actually going to work that out. Maybe this is a little longer in terms of its process than we need to, but I think it's a clear setup, to be honest. So in this case, we would expect to have 19.2 perfect chocolates, and then 1 over 25 times 20, we would expect to have 0.08 flawed chocolates. And I'm doing this in a kind of drawn out way, more than we need to, but I hope it helps. So the amount of money that we earn is going to be made up of 50 times the number of perfect chocolates, plus we get $15 for the number of flawed chocolates. Or what can we say? $50 on average for 19.2 plus $15 for on average 0.08 chocolates. Oh, I'm sorry. I thought that seemed a little low. 0.8. So 0.08 would be, they barely show up, but we know 1 out of 25 should be a little higher for 20 chocolates. Alright, so let's go and work that out. I'm going to work it out on the calculator that I have right here. 50 times 19.2 plus 15 times 0.8. And this should give us 972 pesos. That would be his expected earnings. Okay. Alright, so I think that is good. Okay, next question. Getting a little more challenging as we go on. This one, to be honest, might look intimidating at first glance, especially because logs isn't like a major theme in applications interpretations, but it's essentially a functions question. It's an input-output question, and at least the first part is actually, to be honest, I think it's not too bad. So let's have a look and see what we can do. The pH scale is a measure of the acidity of a solution. Its value is given by the formula pH is equal to negative log base 10, and then we have this H plus. So maybe there's like a lot that could be confusing here, but pH, this is only one variable. This is the scale, the pH scale from like ChemCast. It's how acidic something is. And then this log base 10, that's okay. And then this plus, this is, hydrogen ions. So this plus isn't like an exponent or anything like that. It's just how we write hydrogen ions. Okay, so pH scale is a measure of the acidity of a solution. Its value is given by the formula. Here it is. pH is equal to negative log base 10 of H+, where H+ is a concentration of hydrogen ions in the solution, and it's measured in moles per liter. A lot of information here, but we don't need a lot of this, like this moles per liter, not entirely. All right, part A, they ask us to calculate the pH value if the concentration of hydrogen ions is 0.0003. So this H+ is the concentration of hydrogen ions, and we're asked to find the pH. So if we have an input-output situation, that is, say the pH is related to the concentration of hydrogen ions, we should be able to put this value of 0.0003 into this equation, and then this should give us the pH. And so essentially this is just an input-output kind of question. So let's go ahead and write this out. pH is equal to negative log base 10 of H+. That's our formula. And they tell us that the concentration of hydrogen ions is 0.03. That is to say, in this case, H+ is equal to 0.0003. So pH is equal to negative log base 10 of 0.0003. All right. Let's go to the calculator and work that out. And to be honest, that's all that actually is in this case. Not a bad 2-mark question in some ways. So let's go and write negative. Our log button is right here, so we'll need to go control log base 10, and we want to write 0.0003. And that is the pH, so 3.5228, or 2.288, yes. Okay, let's go back to the document. pH level is equal to 3.52. Not bad. Okay, let's go to part B. The pH of milk is 6.6. Calculate the concentration of hydrogen ions in milk. So again, for a 2-mark question, it's not too bad. It looks more complicated than it may be just because of all the variables, and we have log thrown in and so. But here's our formula once again of H+. So we can put in, for example, a value of H+ like we did before, and then we can get a pH value. This is just a relationship between pH and then the concentration of hydrogen ions. So in this case, we can also put in a pH value, and we can get the concentration of hydrogen ions. And that's exactly what we're going to do in this case. We know the pH of milk is 6.6, and what we want to find is the concentration of hydrogen ions. So let's use our formula. 6.6 is equal to negative log base 10, and then this is H+. Let's go to the calculator and work this out. Actually, to stay here just a little longer, what we can do is we can end solve this. So now let's go to the calculator. So menu, algebra, numerical solve. We've got an equation. We have one unknown. 6.6 is equal to negative log base 10 once again, and we don't need to put H+ because it's just an unknown. We can call it H if we want. We can call it X. I'm going to call it X. So 6.6, the pH is equal to negative log base 10 of X. What is that concentration of hydrogen ions? All right, and it gives us a super small number. So be careful when you see this E. This is the calculator notation, and we've got to convert it a little. So let's go back to the document for a sec. I'm going to write this down exactly as it is. So the calculator told us that it's 2.51189, and then the calculator gave us this E, -7. And what this means is this, we can kind of read this as exponent, or 10 to the negative 7. So the proper way to write this is 2.51189, but it's times 10, whoopsie, times 10 to the negative 7. So the IB won't accept this calculator notation, this E. So just simplify it a little more, 2.51 times 10 to the negative 7. So a fair number of zeros. We would have to move 1, 2, 3, 4, 5, 6, 7 zeros if we wanted to write this out without any kind of decimals. Or sorry, without this scientific notation here. Oops. Okay. All right. Let's continue on here. The strength of an acid is measured by its concentration of hydrogen ions. A lemon has a pH value of 2, and a tomato has a pH value of 4.5. Calculate how many times stronger the acid in a lemon is when compared to the acid in a tomato. Okay, so this is a question which kind of draws on a conceptual understanding of logarithms. You might think that, oh, okay, well, this is 4.5 of a tomato, and a lemon is a pH of 2, and it's like, it's roughly 2.15 stronger. But first off, like, hey, it's a 3-mark question, so chances are there's something more going on here, and really there is. So as best as I can, I'll try to do a quick kind of overview of what logs are and what this pH value means, for example. So I'm just going to do it with, so if we have something like log base 10 of 100, what's happening here is essentially this is saying if we have 10 raised to what power gives us 100. So log base 10 of 100 is actually equal to 2. And in some ways we could have written the same statement as 10 to the power of what equals 100, and then we would still have this value of 10 to the 2. So similarly, if we said, let's choose some different numbers here, let's say log base 3 of 9. Essentially we're saying, okay, well, 3 to the power of what gives us 9? And well, okay, 3 squared gives us 9. Or if we wanted to write it in a different way, we could say, okay, well, 3 to the power of what gives us 9? Well, 3 squared. So if we're looking at logs, I'm going to go just a little more. If we're looking at a certain set of values, in this case, we can't exactly use pH. We could, but I think it would be a little, maybe more confusing. But if we're talking about some value of let's say x, and then we're talking about log base 10 of x, if x is equal to 10 and 100 and 1,000 or 10,000 and so, this would be log base 10 of 10 and log base 10 of 100, right? So these are the x values. So when x is equal to 1,000, we have log base 10 of 1,000. When x is equal to 10,000, it's log base 10 of 10,000. And in this case, we're again asking the same question. 10 raised to what power gives us this? Well, this is equal to 1. 10 raised to the power of 2 gives us 100. 10 raised to the power of 3 gives us 1,000. 10 raised to the power of 4 gives us 10,000. And so, just like our pH scale, if we have something that has a pH of 2 and 4.5, or in this case, we can imagine this is like some pseudo pH scale or something like that. If something has, let's say, a pH of, or pseudo pH of 2 or 3, or let's say this is the sound level or something like that. If something has a value of 2, let's call this, let's call it pseudo pH. A pseudo pH of 2, and this has a pseudo pH of 3. It's not just 1.5 times as high. It's, well, in terms of the original values, it's actually 10 times. So in this case, we can't just grab this 4.5 and divide by 2 and say that the pH is roughly 1.15 times as much, because we're interested in knowing the hydrogen ion, the difference in the concentration of hydrogen ions. All we have is the pH in each of these cases. The pH is 2 or the pH is 4. But we don't know how many times as much or how many times the concentration of hydrogen ions is. So we're going to need to find the concentration of hydrogen ions for both of these and then compare that. So I hope that wasn't too long-winded. Let's go ahead and find out. So pH is equal to negative log base 10. This is H plus. In this case, we know the pH is 2. And we have negative log base 10 of H plus. And then in the other case, we have, I'm going to actually write this down. This is our lemon. Is this too clever? Yeah, it is. Here's our lemon. And then this would be our tomato. There we go. This is pH is equal to negative log base 10 of H plus. Once again, this case, it would be 4.5. Our tomato has a pH of 4.5. And here we go, negative log base 10 of H plus. So let's go back to the calculator real quick, and we'll find the concentration of hydrogen ions for each. Menu and numerical solve. 2 equals negative log base 10 of, let's use x once again, that should be fine. Alright, 0.01. So I'm going to go back to the calculator and just write this out. So H plus is equal to 0.01. And this is the concentration of hydrogen ions for a lemon. Let's go back to the calculator for a sec. Menu, algebra, numerical solve. And let's go 4.5 equals negative log base 10 of, I'm going to use x again. In this case, 0.000032. So I'm going to go back to the document here. 0.000032. Okay. How many times stronger the acid in a lemon is when compared to the acid of a tomato? So if we wanted to say this is pH lemon versus, or sorry, H number of hydrogen ions in a lemon and the number of hydrogen ions in a tomato, how many times stronger? Well, it's H plus of the lemon over H plus of the tomato, which in other words is 0.01 over 0.0000032. So I'm going to work that out in the calculator, or actually the calculator that I have beside me. 2, 3, 4 zeros. Okay. So it is actually 312.5 times stronger. All right. Good stuff. So there it is, question 7. Okay, I think we are ready. Let's see. I see. Okay, sorry, I've just got to draw this back a little. I was just looking at the mark scheme, and in terms of the float, that is to say the number of digits, the number of accuracy, I have this set a little too narrow. So this is a default setting. I'm going to have to go, and a float 6 is is not enough. We're going to need a float 8. Let's get some more digits. This is kind of wild. So let's go and do this same calculation again. 0.03162. That's really weird. That's very, very strange. That's very strange. Because, what does that mean? That means if we don't have enough accuracy, we would get the question wrong. So I was just looking at the MART scheme because I wasn't sure if that was entirely it. But if we don't have enough accuracy, we get a different value. So for example, previously we used 0.00032. Just go back to the document for a sec. So here we have this 0.0032. I'm going to write this out once again in, actually just going to change the accuracy. So not 0.0032, but 3, I'm going to put to 3 sig figs, 316. And so I'm going to change this right here, 32 to 316. And here we go, 0.01 divided by 0.234316. And this is actually going to change our results. So still from 3112 to 316.45 or 316.45. Let's just write it as 46, I suppose. Or to 3 sig figs is 316. That's quite interesting, because if we just use 2 decimal places isn't usually enough. Actually, it's never enough. If we have more accuracy, we usually want to save all our accuracy till the end. But we always want to keep at least 3 significant figures. So 0.032, was that, the final level of accuracy, or was the calculator just cutting us off at that point? It turned out the calculator was just set to provide only a certain number of decimal places. So change the float, get more accuracy, and kind of an interesting question. Almost like a calculator question. Calculator setting question is also important in this case. So there it is. 316 is the proper answer. Alright, let's go on. Question 8. Gustav plays a game in which he first tosses an unbiased coin and then rolls an unbiased 6-sided die. If the coin shows tails, the score on the die is Gustav's final number of points. If the coin shows heads, 1 is added to the score on the die for Gustav's final number of points. Part A asks us to find the probability that Gustav's final number of points is 7. So he plays this game, he rolls a die between 1 and 6, and then he rolls a coin, or flips a coin, and it's either heads or tails. And if it's tails, the score on the die is Gustav's final number of points. If it's a head, then the score on the die, 1 is added to the score on the die. Alright, so what are the chances he gets a 7? Let's actually draw a table for this. So let's go ahead and represent the sample space here. So he can get a 1, a 2, a 3, a 4, a 5, or a 6, and he can also get a heads or a tails. If it's a tails, the score is just a number on the die. So if it's a tails, he gets a 1, 2, 3, 4, 5, or 6. But if it's a heads, then 1 is added to the point. So if he gets, for example, a heads and a 1, then the score that shows up that he records is a 2. And same for if he rolls, for example, a 2. 1 is added to it, and he would have a 3, and so on. So in this case, there are, in this 2x6 table, there are 12 possible outcomes, and we want to know the probability that he gets a 7. So in this case, there's only one way to get a 7, and that is 1 out of the 12 possible outcomes. And all of these outcomes are equally likely. So probability of a 7 is equal to 1 out of 12. For a 2-mark question, we would want to show either a sample space or potentially we can get, the only way to get a 7 is a heads. Probability of 7 is a heads times, and then also the probability of getting a 6. So 1 over 6, and that would be another way to do it. So one of these methods, either sample space or showing multiplication of independent events. Okay. Part B asks us to complete the following table. So the final number of points and the probability. In this case, I think the sample space sets us up pretty nicely. So let's have a look. Here we go. Final number of points, the probability of getting 1 point, well, that only happens 1 out of 12 times. In this case, 2 points happens 2 out of 12 times, or 1 out of 6. 3 is also similarly 2, 2, 2. All of these are 2 out of 12 times, or 1 out of 6 if we're just simplifying. 1 out of 6, 1 out of 6, 1 out of 6, and then probability of getting a 6 is also 1 out of 6, and this is 1 out of 12. Okay, that wasn't too bad. Part C asks us to calculate the expected value of Gustav's final number of points. Alright, so we saw expected value earlier as well when we were talking about the number of perfect and the number of flawed treats. And we had this formula EX is equal to n, the value, and then the probability of occurrence. In this case, we have, well, 7 different things that can happen, and each of them will have their own contribution. So if we're looking at this, we get a 1/12 of the time, plus, well, we can get 2 points, and that happens 1/6 of the time. And we can get 3 points, and that'll happen again 1/6 of the time. 4 points will happen 1/6. So the value and then the probability of getting that value. So if we had like some large value and a high probability of getting that value, then our expected number of points would skew in that direction. In this case, we actually have some symmetry. That is to say, the extremes are both equally likely, and these middle points are also all equally likely. So I guess, what could we imagine? We'd imagine the balance is kind of around this 4, and we can work that out and confirm that. Let's go ahead. And if we type this in, this will be 1/12 plus 2/6, and so on and so on and so on. Let's work it out with a calculator, and you can actually, but maybe I'll just show you as well here. This is perfectly fine. I just want to say this is perfectly fine, and it's not a bad way to do it. It's a good way. But if we also look at this, equal probability of getting a 3 and getting a 5, and the average between 3 and a 5 is 4. So these will cancel out. Same with a 2 and a 6. These will also cancel out, and these will also essentially balance at a 4. And then of course, our symmetry, our overall average, the average number of points that we would be awarded would be, no, that's not a good way to do it. Alright, so if we go ahead and just add up all of these values, then in the end we would get what our initial kind of suspicion suggested, a value of 4, the expected value. So on average, we can expect to get 4 points. Alright, let's go ahead to number 9. Usually get a little more challenging here. This number 9 I actually think is okay still. Alright. A marathon is a race over a distance of 42.195 kilometers. 2 runners, Efje and Shume, are training to run a marathon. The 2 runners train in different ways. Efje runs 5 kilometers on the first day of training and then increases the distance she runs by 2 kilometers on each subsequent day. Shume runs 5 kilometers on the first day of training and then increases the distance she runs by 13% on each subsequent day. Determine which runner will be the first to run the distance of a marathon on a particular day of their training, and state on which day of their training this one will occur. So what do we want to do? Which runner will be the first on a particular day, and state on which day that will occur. Okay. So if we're looking at Ephia will have, what do we have? Let's say this is the number of days, and this is, let's say, the distance that she's run. So Ephia runs 5 kilometers on the first day, and then she runs 2 kilometers on each subsequent day. So the second and the third and so on. She'll run 7 and then 9. And I'd imagine you can see this already. This is a linear sequence. She's just adding 2 kilometers. And then eventually she's going to get to this 42 kilometer. And what about for Shumei? So we know that this is arithmetic. And what about for Shumei? For Shumei, how is the number of days and the distance related? On the first day, the second day, the third day. Shumei also on the first day runs 5 kilometers. And on the second day, he runs she runs 13% more. So in this case, she's not just running 5 kilometers, she's running 13% more. So 100% of what she did, that 5 kilometers plus another 13%, or 113%, or 1.13 times as much. So 5 times 1.13, she runs roughly 5.65. And then further on that, it's another 1.13, and she runs 6.38 on the third day, and so on and so on. So essentially what we'll have is we'll have someone, this is a kind of classic, this is the kind of case of arithmetic growth versus exponential growth. And the question is, okay, exponential always overtakes linear eventually, but will it be before? Who will reach this goal of 42.195 first? That's the question. So let's go ahead and see what we can do. A few different ways that we can actually do this. We can use the graphic calculator. That actually might not be a bad way to do it, but let's see. Let me just write geometric here. I think if we want to use the graphic calculator, we're going to need to find a formula for each. So let's go ahead and find the formulas for each first. That is to say, something that describes the distance that Ephia runs and Shumei runs. All right, arithmetic sequence. We can go to our formula booklet and check out the formulas for each. So here we are. Nth term of an arithmetic sequence, this is term 1, n, term number, and then common difference. So what we're going to need is, we're going to need the first term and then the common difference. And if we're talking about a geometric sequence, we're going to need the first term and the common ratio, what we multiply by to go from one term to the next. So let's go ahead and write out those formulas. un is equal to u1 plus n minus 1 times d. u1, the value of the first term is 5, plus n minus 1, common difference is 2. Alright, let's go to the geometric. un is equal to u1, value of the first term, times r, the common ratio. What are we multiplying by to go from one term to the next? It's equal to 1.13, and then raise this to the power of n minus 1. So let me just to be consistent, I'm going to move this down just slightly and write this out. u1 times r n minus 1. Okay. Alright. So we've got a formula for each. I'm worried that this graphic will be potentially, it won't be too complex, but I think there's other ways to do this. So let me show you maybe the first potential way. We've got a formula for each, and it tells us the distance that they'll travel when n is equal to 1, 2, 3, 4, that is to say the first, second, third, fourth day, and so. And essentially these sequences, or these formulas, relate inputs and outputs like all of our functions, essentially. So if we want to find how long it'll take for one of these individuals to reach 42.195, we can treat this as a kind of input-output function. So 42.195 is the goal. And the question is, okay, if this is our sequence, what is the term number that will make that true? That is to say, what is the value of n that will make this true? On what day will this person reach 42.195? In the same case, we can do something similar for the geometric sequence. That is to say, when will this person reach 42.195? If this is the formula that tells us n minus 1. So if we put in certain values of n, what is the n value? What is the value of n that will make this true, that will turn this into this, essentially? So we've got two equations. We can n solve, find the value of n, that is to say, find how long it will take each of them to reach 42.195 kilometers, and then we can see who is going to be the first, who gets there the quickest, I suppose, or the soonest. So let's go new document, and let's go into our calculator screen. Here we are. Let's go numerical solve. 42.195. 195. Oops. 195 equals 5 plus, we'll say n minus 1, and then we'll say this is equal to 2, and then we'll solve for n. Okay. So after 19.598 days, Efya will be running a marathon. Algebra numerical solve 42.195 equals 5 times 1.13. Then we'll raise this to the power, let's put brackets just in case, just be mindful. And then we'll solve for n as well. And in this case, Shumei will run a marathon, or run the distance of a marathon, after 18.45 days. So let's go back to the calculator for a sec. And so in this case, the number of days it will take Efya will be 19.598. So I forgot to put a decimal there. And the number of days it will take Shumei will be 18.45 days. So, on which runner will be the first to run the distance of a marathon, and on what day? Well, it actually won't be until the 19th day for Shumei, because she got close on the 18th day. She doesn't really practice on the 0.45th day, so it's not until the 19th day. And Efya similarly won't get there until the 20th day. So, who gets there first? It is Shumei, and when does she get there? She gets there on the 19th day. Alright, and there we have it. Yeah, I think that's good. Do we want to do the graphing way, or I would say, maybe it can really quick. Alright, let's go. If we wanted to, we can go into our graphing calculator and put in, this is Shumei's results. And then I'm going to actually, to be honest, I'm actually just going to copy paste this. And let's go in menu, graph entry, function, menu, graph entry, function, there it is. Calculator doesn't like anything but x's. There it is. And there is Epheus. Okay. 5 plus x minus 1 times 2. Something bad happened here. This is something that says make sure to use brackets. Come on now. Okay, so I guess it's okay. Alright, and what is the point of intersection? I'm curious. Potentially something went wrong. Okay. This is interesting. So if you were to get this, and you would say, oh, okay, they intersect at the point of 1. Yeah, because they both start on the first day at 5 kilometers. So it's not, oh no, something went wrong. We just need to zoom out, actually. Zoom out. And then find the other point of intersection. This might actually provide a little more information. So on the 17th day, 17.666, we have Shumei overtaking. And when does he overtake, or she overtake, sorry? At 38.331 kilometers. The last way to do this, if you're like a guru at the calculator, the graphing calculator, then maybe this is all, great. Analyze graph. Let's put in, graph entry. Let's put in another function, 42.195, the distance of a marathon. So this is the distance of a marathon, and we see who gets there first. This is time, right? The axis. The first day they go 5, and then a little more. Who gets there first? It is Shumei. Shumei gets there on the intersection between these two, between this one and this one. Shumei gets there, this is exactly what we saw. On the 18.45 days, Shumei gets there to 42.195. Maybe if you're comfortable with the graphing calculator, then by all means, you can use the graphing calculator. I would just say make sure to sketch this. Sketch this, not necessarily the point of intersection, but this one in particular. That is to say, this 18.45 and this 42.195. Graph the functions, find where they intersect. Shumei is going to increase after that point, and then you can also label this point of intersection. Alright, let's go back to the document. Potentially the first way was easier. Alright everybody, here we are on question 10. We've made it this far. And to be honest, these last 3 questions, 10, 11, 12, are quite challenging. Let's work through them and just give it our best effort. Let's go. The gradient of the normal to the curve y equals ax squared plus bx minus 10 at the point t, 2, 4 is negative 1, 3. Let me just change this here. Alright, calculate the value of a and the value of b. Lot going on here. I'm going to give some kind of conceptual background just to unpack these terms, and then we'll make our way through it. So super, I think, abstract, especially for applications interpretations. So what is actually going on here? First, they're telling us that the gradient of the normal to the curve of this function here at a certain point is negative 1/3. So let's unpack that statement first. So what are we talking about when we're talking about the gradient of a normal, the gradient of a curve, and then the normal to a curve? So let's just imagine some function like this. And what are we talking about if we're talking about the gradient of the curve at a given point? We're talking about the slope of a line, or the slope of a tangent line at a given point. So this would be our tangent line, for example. And we might say, okay, well, what's the slope at this given point, the instantaneous rate of change? And that should already potentially bring to mind some concepts like the derivative. The instantaneous rate of change at a point, the slope at a given point on some function. This is our tangent line. And we could say, just for example, let's say this is maybe m is equal to, I don't know, maybe it's 3 or something like that. Actually, let's make it even a little better. Let's say it's, 3 over 2. 3 over 2, maybe 1/2. Maybe it's something like that. All right. And if this is the slope of our function at a given point, or the slope of a tangent line, what are they talking about here when they're talking about the gradient or the slope of a normal to a curve at a certain point? So we can imagine this is some point, this is the slope of the tangent line. What are we talking about when we're talking about the normal to a curve? The normal is not tangent, but rather a right angle at some given point. So this would be the normal. This would be the normal to a given curve. And they are related to one another. We see that if these things are indeed perpendicular to one another, just like when we're talking about perpendicular lines in coordinate geometry, the normal to a point would be m perp. So if we know the slope of a line is 3/2, what is m perpendicular? Remember, the trick to this was switch the top and the bottom and multiply by -1. So in this case, the perpendicular, the normal to a given curve, in this case, in this hypothetical case, would be -2/3. And that would be the slope of the normal to a curve. So in this question, for example, they're not being so straightforward in saying here the slope of a line at a given point is -1/3. They're telling us the normal to a curve, so we're going to have to work with that first because we're only given this. And of course our derivative deals with tangent lines, so instantaneous rate of change at a given point. Doesn't give us the normal right away, so we're going to need to convert it. Alright, that's the first little piece of the puzzle that we're going to need. The second piece is, what is this function itself, and what are they asking us to do? 7 marks, no scaffolding. They're just kind of throwing us out into, not necessarily the deep end, but they're just saying, here it is, find your way. So what is this y equals ax squared plus bx minus 10? So this is itself a quadratic. We know it's a quadratic because it's raised to the power of 2, this highest degree term. And so what does that mean? That means that our function has the shape of a parabola. Maybe it opens upwards, maybe it opens downwards, but it has the shape of a parabola. We also know that the y-intercept is -10. So the y-intercept is when we cut the y-axis. That's when x is equal to 0. And so when x is equal to 0, if you were to sub that in here, this would go away, this would go away, and you'd just have this -10. So you'd have this coordinate point 0, -10. And on this hypothetical graph, I guess, that would be, okay, we're cutting this axis, the y-axis, at 0 and -10, hypothetically. Okay. So we know a few things, and lastly, I'm just going to clear this up a little, so we don't need this exactly anymore. We're asked to find these two values of a and b. So what is the approach? We have some hints. They're talking about the gradient or the slope of a line at a given point, and that tells us that calculus may be needed here because we know the derivative. The derivative itself gives us the slope of a line at a point, or the gradient, or in other words, the instantaneous rate of change. This is what the derivative does for us. So it tells us that calculus might be needed, and then we want to find these values of a and b. So what can we do? Without actually just giving the answer, let's try to work through it and see what we can do. So it tells us that calculus is going to be needed in some way, or at least it suggests that it might be because we have this slope of a line at a point. So let's take this function itself, this y equals ax squared, oops, let me get that a little larger, this ax squared plus bx minus 10. Okay, we know the slope of a line at a point is given by the derivative. We input some value of x into our derivative, and then out pops the slope of a line at a given point. The instantaneous rate of change at that given point is whatever the output is in that case. So let's find the derivative of this function right here. And remember, these two things are equal, this f prime of x and dy dx. So we could use either notation. Here, let's keep the notation that they have, and let's use dy dx. All right. So dy dx is equal to, let's use our power rule. Remember, our power rule is given to us in our formula booklet. I'm going to write it real quick in the top corner here. If f of x is equal to x to the power of n, f prime of x, that is to say the derivative, what do? We take this exponent, bring it out in front. Now it's n times x, and then what happens to the exponent? It's reduced by 1. This is given to us in our formula booklet, so if you need to ever draw on it, it's there. So let's follow that same procedure here. Take this exponent of 2, multiply it out in front. And so we have 2ax. X used to be 2, now it's 1. Don't really need that 1, so let's leave it off. Plus, here there's a 1 right here. Don't really need it. If we remember that the x just kind of falls away when we take the derivative, that might be helpful as well. But b times 1 is b, and then the x falls away. And then constants themselves go away as well. So this is what our derivative looks like now. And if you're wondering, and the IB often does actually throw these kind of questions in, like, hey, what about this a and b? Why didn't we have to do anything with that? The values of a and b are just going to be plain numbers. They might be fractions or decimals or whole numbers or negatives and so, but they're just plain numbers. They're constants. Whereas this x, the x is a variable. We can throw in a number of different values for x, and it'll output a certain y. But this a and b, these are constants, values that are part of the function that we just don't know yet. So let's go ahead and see what we have here. We've got this derivative, dy dx is equal to 2ax plus b. And I'm going to do one thing just because I think it's going to be a little more helpful. I'm going to change this dy dx. Remember we said the notation were the exact same. So instead of this dy dx, actually I'm going to leave it, just clean it up a little. Let's rewrite it as f prime of x, because these are effectively the same notation, or sorry, different notation for the same thing. And we have 2ax plus b. All right, so we know the derivative is equal to 2ax plus b, and we also know that the gradient of the normal to the curve at some point is negative 1, 3. So let's make use of that. I'm going to draw a little graph just to help illustrate what's going on. So here we go. Remember, let's make use of this as well. We don't really need to, but I'm going to draw it just for consistency's sake. So here's the point 0 and negative 10. And I'm going to draw a quadratic because it is going to be in the shape of some parabola. And I'm going to draw it just like this. That's not terrible. That'll work. All right. And we've got this point 2, 4 right here. So let's put that right here. Let's put this point 2, 4. I hope that's legible. So we have this point 2, 4, and they tell us that the gradient, the slope of the normal to the curve, is negative 1, 3. So that means I'm going to draw the tangent first, even though we don't know what it is. Let's do something a little better. That's better. Okay. So here's our tangent, and let's draw the normal. So the normal, we know, occurs at a right angle. So there's our normal. I'm going to draw it once again. I'm just going to say normal, just so we can keep in mind. So there's the normal, and what do we know about the normal? We know that m, perpendicular, because the normal is perpendicular to the tangent, is equal to negative 1 over 3. And this tangent line right here, that's what our derivative gives us. If we put in, let's say, f prime of 2, an input of 2, our derivative is going to give us the slope of a tangent line. And right now, we just know the slope of the normal. So let's go and write here, if we have m perpendicular is equal to negative 1 over 3, then what is m? Well, we know that if we switch the top and the bottom, multiply by negative 1, then we'll have m. So let's switch the top and the bottom. 3 goes on the top, 1 on the bottom. Now it's negative 3 multiplied by a negative, and it just turns into 3. Okay, so m is equal to 3. So the slope of the tangent line is equal to 3 at this point when x is equal to 2. So I'm going to write that out right here. I'm going to write this out. So what does that mean? And I'm just going to throw a bunch of, not a bunch, but like some different kind of notational ways to represent this. So we have f prime of 2 is equal to 3. What does that mean? That means the derivative, the instantaneous rate of change, the slope of the tangent line when x is equal to 2 is equal to 3. And that's what we have here. Okay, so let's go ahead and use that. We know that when x is equal to 2, the derivative, f prime of x, is equal to 3. So we've got a function here. We know an input, we know an output. Let's put that into our equation and see what we can do. So we know that f prime of x, the derivative, is equal to 3, is equal to 3 when x is equal to 2. So that's what we know. The derivative is equal to 3 when x is equal to 2. Let's put in 2 into our function, and we'll put in 3 as the output. Okay, this is 2 times 2 is going to be 4. Let's clean this up, and now we have 3 is equal to 4a plus b. And this is actually important, so I'm actually going to give it some space, and I'm even going to call it something. I'm going to call it equation 1, maybe even give it a special color. Alright, so this is equation 1, and it is actually nice and important, and it's a step along the way. So, we've made some good progress. So we've got one equation, but again, the problem is we have a and b, and we have 2 unknowns that we want to solve for. So if we had another equation, then we would be able to solve for these values of a and b. At the moment, a and b can take a whole range of values. We could find a value for a. For example, a might be equal to, let's say 1, and then b could be equal to -1. But that's not the only possibility. There's tons of other combinations of a and b that will make 3. So we need to constrain this a little more. So we need to find one more equation. In that case, 2 equations, 2 unknowns, we can always solve. By and large. Alright. So where are we going to find that other equation? Here in our original setup right here, they told us that y is equal to ax squared plus bx minus 10. And we also have a point on this line. We have this quadratic right here. We already have an x, y value that's on this function itself. And so what does that mean? That means that if we have a point on the line, it's a solution to the equation. It already balances the equation. So if we put in x, we know what y should be at that time. And then the only things we won't know is a and b. But that's okay because we just end up with another equation with a and b. So let's go use that second part right here. Make sure I can see it. Y is equal to ax squared plus bx minus 10. Alright. Y is equal to ax squared plus bx minus 10. Is that correct? Yes. Okay. And let's put in these values of 2 and 4 once again. So x is equal to 2, y is equal to 4. So here's 4. X is equal to 2. And x is equal to 2 once again, minus 10. Alright. 4 stays the same. 2 squared is 4. 4 times a is 4a. B times 2 is just 2b. And this is -10. Alright, that is another big step. That is equation 2, and that is the final equation that we were looking for. So we have 2 equations, 2 unknowns, and now we can finally solve. So a lot of work has been done. Let's go ahead to the calculator and put these 2 equations in to our linear solver, and then we should be able to find the solutions for a and b. Okay, so going back to the calculator here. Here we are. Where are we now? Let's go calculator, menu, let's go to algebra, and we have a system of linear equations. They're linear because they're not raised to a square or a cube power. What do we have? We have two equations. Just to make it easier, I'm going to actually write this in A and B because that's what we have. Right, and now we have our two equations, we have our unknowns, and let's input the equations. The first one was 3 is equal to 4a plus b. And the second one was 4 is equal to 4a plus 2b minus 10. All right, let's make sure these are the same because we did a lot of work. Let's not have any errors now. All right, there it is. A is equal to -2, b is equal to 11, and I'd imagine if you're writing a test, that's got to be, extremely satisfying. So let's go back to the document here. Calculate the value of a and b. Here we are. A is equal to -2, and b is equal to 11, and there we are. There we are. That's it. Okay. So I would just say one last thing, because this is a challenging question, and it's just 7 marks, and they don't really scaffold it or break it down. If you approach this on a paper 1 and you're not sure what this is, but you see gradient of the normal is -1/3, on the mark scheme itself, I'm not sure if I can, maybe I'll bring it up. On the mark scheme itself, there's, for example, let me just go back to here. If it tells us the gradient of the normal, for example, is -1/3, and if there's even just the inclination that, okay, we might need to find the tangent, even if we have m perp is equal to -1/3, m is equal to 3, this is potentially 1 mark. This is 1 mark, and it's something. It's not something to be kind of just, if you can maximize your process, you'll always put yourself in a better position to be successful. Even here, 2, 4, substituting these values of x is equal to 2, y is equal to 4 into our original equation is going to be another mark. So here's actually the mark scheme right here. I'll bring it up on the screen. So we see 3 seen at any stage of their work. That's one answer mark. Taking the derivative is a method mark and an answer mark. So if it's saying, hey, gradient of a line at a point, that seems like there's the derivative. You're not sure how the pieces fall together, but there's some kind of inclination or inkling that, yeah, maybe the derivative is involved. Taking the derivative, and then even the gradient of the tangent line, or the reciprocal of the normal. This is already 3 out of the 7 marks on a really hard, I think, potentially really, really challenging question. So that's not bad. That's not bad. Okay. All right. Let's move on. Okay. Here we go. 6 mark question. I think this is actually a little lighter than the previous one. I think it's just a very nice question. A sheep is in a field in the shape of a triangle. ABC. So here's the sheep. AC is 21 meters, AB is 15 meters, and CAB is 78 degrees. A goat is in an adjacent field in the shape of a sector of a circle with center A and a radius of 8 meters. The fields are shown in the diagram. Determine which animal, the sheep or the goat, is in the field with a larger area, and state how many extra square meters are in this larger field. So first things, there's 2 parts. First, which animal is in the field with the larger area, so we're going to need to calculate the areas of both. And then lastly, how many extra square meters are in this larger field. So that seems like a fairly straightforward calculation, so let's not forget about that part as well. Last thing as well, they give us a few values here. They tell us AC, AB, and CAB, but not all of these are on the line. And they also tell us the radius, or in this diagram. So let's label this, and that's going to be helpful. So AC is equal to 21. So I'm going to put that here. And AB is equal to 15. I'm going to put that here. And they also tell us that CAB is 78. That's there. And the radius is 8. So I'm going to write that out here. The radius is equal to 8. Actually, I'm going to draw it somewhere else so it doesn't clutter this up. I hope that's not too confusing. Alright, so the radius is equal to 8. R is equal to 8. Okay, so which animal, the sheep or the goat, is in the field with a larger area? Okay, this isn't actually too bad. So let's go and deal with the sheep first. So here's the sheep. They're in this triangular pen, I suppose, this triangular field. And we have an angle, and then two side lengths. And we have an included angle. That means an angle between two side lengths. In the world of non-right angle trigonometry, if we need to, or if you need to jog your memory or so, we can go to, where is our geometry? Here it is. Right angle trigonometry, we have these three formulas, right? Sine rule, cosine rule, and, of course, the area of a triangle. Half AB sine C. If this is A and this is B, we need that included angle, the one that is between the legs of the two other side lengths that we know. And that's exactly what we have here. So we have AB, we have those two side lengths, and the angle C in between. So let's use the area of a triangle right here to find the area that the goat is in. Okay, and I'm going to write this on this side, and let's say this is, the sheep. Sheep, what am I saying? Okay, area is equal to half AB sine C. Area is equal to half A, doesn't matter the order, 21 times 15 times sine 78. Okay, I'm going to go to the calculator real quick. Here we are. Let's go and write out 1/2 21 times 15 multiplied by sine 78. Make sure that we're in degrees. Here we are, of course. And there we go. 154.058. I'm going to go back to the document and write that out. 154.058. And I'm going to write AS for area of sheep. Okay, and let's give the goat maybe the green. Alright, so AG, area of the goat. And what do we have for the area of the goat? We know we have this radius of 0.8, isn't it 0.8? Sorry, R is just equal to 8. So it's 8 meters. But we don't have a whole circle. We know the area of a circle is just given by pi r squared, but we don't have a whole circle here. We only have a part of a circle. We're missing 78 degrees out of a full 360 degrees. So, I mean, just by intuition, we can say, okay, well, what do we have? We're missing 78 out of 360. 360 would be a whole. But if you want, we can also go to our formula booklet and we can look at this, the area of a sector. So what is the area of a sector? The sector, remember, is a part of a circle. Is theta divided by 360, so the angle that we have out of a full rotation of 360, and then times, of course, our pi r squared. So what is the fraction of the whole that we have? Okay, so let's go ahead and work that out. So pi r squared is the whole. We don't have the whole. We're missing 78. So what is our theta value? Theta, that is to say the angle that we rotate through, the fraction of the circle that we have. We don't have 360. We have 360 minus 78. So we don't have the whole part, just a fraction. We only have, and I just typed this in, 282 degrees out of our 360. That's a fraction of the circle that we have. So let's go and look at the area of the goat. We know it's theta over 360 times pi r squared. Theta over 360, it's 282 over 360 times pi radius of 8 squared. Okay, let's go to the calculator and write this in. Okay, oops, don't need that. Here we are. 282 over 360 times pi, and then the radius was 8 squared. Okay. And there it is, 157.499. That should be reassuring as well. If this was suddenly like 4,000, or one of these is like 12 times as large as the other, then it would be some kind of indication that something has gone wrong. But these are fairly close, which should give some confidence as well. Let's go back to the document and write this out. 157.499. Okay. Last part, remember, is determine which animal, the sheep or the goat. So the sheep or the goat is in the field with a larger area, and state how many extra square meters are in this field. I should just say, sorry, just while I'm doing this, remember at the very beginning of an exam, it does say that all answers should be placed within this box right here. Examiners are only required to mark within this section right here. I'm doing this section right here, unless otherwise stated, unless it's filling in a table or something like that. I'm doing this here just because I think it's helpful to see the diagram, but when you work this out in your actual exam, put all relevant information within this box, of course. Okay, so determine which animal, the sheep or the goat, is in the field with the larger area. Well, we know that, what do we know? We know that the area of the goat is greater than the area of the sheep. And what does that mean? 157, whoops, let me get the same colors. 157 point, let's just say 157.5 is greater than 154.1. Okay, and by how many extra square meters? By how many extra square meters? That seems like a pretty straightforward calculation. That's just going to be area of the goat minus area of the sheep. So area of the goat minus area of the sheep. 157.499 minus 154.058. I'm going to work that out on the little calculator that I have beside me here. 157.499 minus 154.058. And the answer is 3.441, or I'm going to just round this to 3 sig figs. 3.441 or 3.44. It's possible that along the way, some rounding here or here or here or here may create some deviation from the mark in the, let's say, the solution book. So I think sometimes it's actually, I think it's helpful to write 3 sig figs, 3 sig figs, 3 sig figs. All right. Okay, let's keep going on. We've made it to the final question. All right, here we are on the last question, question 12. I don't believe there's anything else after this. Okay. So, last question, they get increasingly challenging as you go on. We'll work through this, and we'll get through this, but I would just say if you're working through this and it's a timed exam, and so 8 marks, they get increasingly difficult. I think it's always a good strategy, maximize process marks where you can. Of course, if you can get to the end of it and your foundations are strong and you've got a good understanding, absolutely. But look for the entry points as well and maximize process where possible. All right, here we are. 8-mark question. A company is designing a new carpet. The intended design of the carpet is in the shape of a rectangle with a semicircle at each end. So there's this rectangle here, and then there's a semicircle, a half circle here, a half circle here. The width of the rectangle is y meters, and the diameter of each semicircle is x meters right here. X is greater than equal to 0, so it's got to have some diameter, and y is greater than or equal to 0, which means that this y could potentially disappear. This width, I mean. The company has decided that the perimeter of the carpet will be 20 meters and would like to maximize its area. So the perimeter going all the way around is going to be equal to 20, and they want to maximize the area. So it tells us that potentially, or likely, this is going to be some kind of optimization question. So often these kind of optimization questions, you take some dimension and then you compare it to the area. So you vary, let's say, the radius, or let's say the width, and you plot area against the width, and you say, okay, what is the point where it maximizes the overall area? So it seems like this is an optimization question. Okay, find an expression for the perimeter in terms of x and y, and I realize this is actually a 1-mark question, which is somewhat short, I guess, for what I think it's asking, but anyways. Perimeter, we know, is equal to 20. So we have 20. And what is the perimeter made up of? It's made up of a y here and a y here. I'm actually going to color code it. Is it necessary for a 1-mark question? I mean, obviously, I probably won't have the time to do this on a test. But this would be 2y plus, and then what else is the perimeter made up of? It's made up of this half circle here and this half circle here. All together, 2 half circles make a whole circle. What is the perimeter, or we'd call it circumference of a circle? It's given by 2 pi r. This is in the formula booklet as well. So here's half circle, here's another half, makes a whole. What's the perimeter of that? It's given by 2 pi r. And we can't actually just put that in because the radius, or our variables, are only in terms of y and x. So the radius, distance from the center to the edge, in this case is not all x, it's just 1/2 of an x. So in this case, circumference is 2 pi r, yes, but it's 2 pi, and the radius is 1/2 of an x. So let's add that in. Is 2 pi times 1/2 of an x. You can clean this up just a little. 20 is equal to 2y plus, these things are all being multiplied. This is 2 times pi times 1/2 times x. And order of multiplication doesn't matter, just like 3 times 5 times 2 is equal to 2 times 5 times 3. So we can actually multiply 2 times a half. 2 halves make a whole. This is just going to be pi x. Alright, so there is our expression for the perimeter in terms of x and y. Alright, so they're not asking to find values of x and y, just write an equation of the perimeter in terms of x and y. So perimeter is equal to 2y plus pi x. Okay. Show that the area a meters squared of the carpet can be expressed as a is equal to 10x minus pi x squared over 4. 3-mark question, so this is a big one here, or fairly. So let's go ahead and work this out. So let's first ask, what is the perimeter made up of? Or sorry, not the perimeter, but the area. So the area is going to be made up of this rectangular portion, and it's going to be also made up of these parts right here, these semicircles. So area I'm going to write it out right here just so we can still see everything else. That's not good. Let me just do that. Just cordon off some area. All right. Here's part B. So area is equal to, well, this rectangular portion, we know that, should we do this? Should we do this? Yeah, let's do it. Okay. We know this rectangular portion, the dimensions are x and y, right? So area is just going to be, of this rectangular portion, it's just going to be x times y. And it wasn't too bad. And then what about these semicircles? So we know we have, well, this half semicircle plus another half semicircle, the one on the left and the one on the right, or one whole circle. And the area of a circle is equal to pi r squared. So if we want to write this out, we also know that the radius is equal to 1/2 x. So we're going to need to do that. The radius, we're going to need to substitute for half of an x, because that's what the radius is. So pi times y, and then this is going to be pi times 1/2 x squared. I'm just going to clean this part up just a little. So what is 1/2 x times 1/2 x? I'm going to write it here. I'll write it up actually in the top left. So 1/2 x squared is equal to 1/2 x, of course, times 1/2 x. 1/2 times 1/2, a half times a half. You can put this on your calculator if you want. That's going to be a quarter. And then x times x is x squared. So this is going to give us 1/4 x squared. So I'm going to clean this up. I'll rewrite it actually. Area is equal to pi times y plus 1/4 x squared. All right. Good. But it doesn't yet look like this. All right. We've got this pi x 1/4, kind of, but there's a negative out in front, so it seems like we might be on the right track. But if we look here, it's just in terms of x and just in terms of x. Here we've got this y. We've got this y that we'd like to get rid of. And how can we do that? Well, if we know that, for example, 2y plus pi x is equal to 20, if we have one other equation where y and x are related, we can rearrange this equation right here and get y all by itself. And if y is equal to something, then that means that y is that thing. And we should be able to substitute or replace y with whatever we have the equivalence of y written. Whatever the equivalence of y is, we can say. All right, so let's go back to this part right here. This 20 equals 2y plus pi x. I'm actually just going to take it, and can I copy this? I cannot. Okay, I'll write it out. So we have 20 is equal to 2y plus pi x. We want to get y all by itself. Let's move this over, and then we'll have 20 minus pi x. What we're doing is we're taking away pi x from both sides. And this is 2y. We don't want 2y, we just want a single y, so let's divide both sides by y. Remember, divide by 2. Divide by 2. And what does that mean? These are going to cancel out, and we'll have y is equal to 20 minus pi x over 2. So y is equal to 20 minus pi x over 2. Okay, I'm actually just going to switch this around, just because, to be honest, I don't know, for myself, it just looks better. So y is equal to 20 minus pi x over 2. This is good. This is good. And we can substitute already. I'm just thinking I'm just thinking it might be helpful if we break this up into two terms. So just like, let's say 5 plus 3 over 2 is the same as 5 over 2 plus 3 over 2. Actually, often we go like this and then into the reverse if we create a common denominator. We can do the same thing here and break up this equation into two different terms. And I think that's actually going to be helpful. So y is equal to 20 over 2 minus pi x over 2. These things are equivalent, and what that does is if we see that this 20 and this 2 is related, it helps us potentially simplify things just a little. So y is equal to 10 minus pi x over 2. All right. So y is equal to this. Y is, right? That's what an equal statement is. Y is this. And if y is equal to 10 minus pi x over 2, we should be able to substitute it into this equation here. So wherever we see an x, let's replace it, wherever we see a y, let's replace it with 10 minus pi x over 2. And then we still have this 1/4 x squared. Okay. All right. It's getting close. It's not quite there yet. We see that we're kind of approaching this 10x, and so now, if you remember, we're going to need to do some distribution. So remember, if we have a, b plus c, we need to distribute ab plus ac. Let's do that here. X times 10, and then x times pi x over 2. Area is equal to x times 10 is 10x. X times negative pi x over 2 is going to be negative pi. X times x is x squared. This is going to be over 2. And then we still have this. I'm going to rewrite this. 1/4 of x over 2 is just going to be x squared over 4. Okay. Now we've got these fractions right here. This pi x squared over 2 and this x over 4. So pi is just a number, 3.1415, so on, so on, so on. But it is just a number. So we can add these x squareds and so on together. So let's go ahead and do that. I'm just looking at this actually. I see this pi x squared here, and I was thinking, where did that pi x squared? Should this not be a pi x squared then, if you want to make it look like this? And it looks like on this step, this half x squared turned into 1/4 x squared, but I forgot to write the pi here. So I'm going to bring that back. I'm not sure if that happened up here. I took this 1/4 x, but forgot the pi. So I'm going to bring that back. This is 1/4 pi x squared, and 1/4, bring that back, 1/4 pi x squared, and then what does that mean? That means this is also pi x squared over 4. Okay. Let's create a common denominator between these two. So area is equal to 10x minus, multiply the top and the bottom by 2 if we want to create a common denominator. We have negative 2 pi x squared over 4 plus pi x squared over 4. This is some pretty heavy algebra for applications interpretations course, I think. So we've got a pi x squared, and someone's taking away 2 pi x squareds from us, so we actually have a negative pi x squared. This 2 pi x squared over 4 and this pi x squared over 4. Pi x squared, someone takes away 2 pi x squareds from us. Now we only have, well, I guess we would owe them a pi x squared. So here we have pi x squared over 4. Okay, and that is what we wanted up here. 10x minus pi x squared over 4. Okay. Last two questions, And to be honest, I was looking at this question earlier, and I think that sometimes, especially on paper 2, we can look for entry points. Maybe if this question is kind of bizarre, and this is the most complex of the subsections here. But this one, find the perimeter. Perimeter is just equal to 20, and it's given by 2 y's, and then this curved surface. That's approachable, I think. And this part right here, dA dx, right? This is the derivative. This is the derivative. This, I think, is a potential entry point, because they give us a, they give us some function right here, and they're asking us to take the derivative of it. So this is potentially an entry point where we didn't need to solve for b. We can just start actually at part c and find the derivative of this function. And then as well, when we get to it, we'll see that this is something that stands alone. Even if all of these 3 were completely kind of bizarre, D itself has its own entry point, where the area is a maximum. We have to watch out for some of the words, but I think there are potential entry points within this very challenging question. All right, so find dA dx. I'm going to need a new page. So area is equal to, I'm going to use this one up here, even though they are the same. This is what we could have done. 10x minus pi x squared over 4. 10x minus pi x squared over 4. Okay. Area is equal to 10x minus pi x squared over 4. Alright. And they're asking us for dA dx. Usually if we have something like y is equal to 2x squared plus 4x and we're asked to do dy dx, we want to take the derivative of y in terms of x, and then we work on this part right here, this variable x. We're going to do the same thing here, except our function is in terms of a. So we're still going to take the derivative in terms of x. So x is to the power of 1. It's not, well, we know what happens there. Let's multiply out in front. Or, if we want, we could say the x just falls away. So this is just 10. Minus, and then we say, okay, well, this is pi over 4 out in front. But this itself is just equal to negative pi over 4 times x squared. This thing is just a number. When we take the derivative, we're interested in just the variable. And so we can still use the same operations and procedures as we've been using in the past. So we've got this pi out in front. We're going to take the exponent, multiply out in front, and so now it's going to be 2 pi. X used to be 2, now it's only 1, and we still have this 4 out in here. Okay, and to be honest, that's a nice 2-mark question. I'm going to clean it up just a little. dA over dx, 10 minus 2 over 4 is just going to be, well, 1/2. So it will be pi x over 2. Essentially we did this, right? We said this is going to be 2 and this is going to turn to 1. If we simplify 2 over 4 to 1/2. Okay, there it is. That's our derivative. Not bad. Not bad at all. Last question. Hence, find the exact value of x for which the area is a maximum. So, just draw your attention to maybe 2 things. This hence is an important word. It means that, okay, you've taken the derivative, now use this derivative to find the exact value of x for which the area is a maximum. So they want you to use the derivative. This hence means make use of that information above to then solve. If we didn't, or if you weren't able to solve for this derivative, it doesn't mean that you can't actually find the area. You could just plug this into the calculator, for example. Area against x. This looks like, to be honest, it actually looks like it's just going to be a quadratic that's going to open downwards. And you could just find that maximum point, and you'll get 1 out of 2 marks. I'm not saying that's the optimal thing to do, but I always think it's a good strategy to maximize your process marks. So here's a function. It's area against x, graph the function, find the highest point, and you will get 1 mark for this. You're not using the derivative, but you will get 1 mark for the area. Okay, let's use the derivative, however. That's what they're asking us to do. Let's label this as C. I believe it was C. And let's go to question D. So we know that the derivative dA over dx is equal to 10 minus pi x over 2. And, sorry, pi x, is it pi x? 10 pi x? Yes. 10 pi x over 2. And if we look at our original function right here, this 10x minus pi x squared over 4, these are just numbers, and this is just a number as well. We have this x raised to the power of 2, which means that it's going to be some kind of quadratic, and maybe it looks something like this or so. And so we have area as a function of x. And if this is our function, area as a function of x, we could plot this, as we just said. We could plot this into the calculator and find the maximum. But how can we use the derivative to find the maximum? The derivative can be used to find the maximum because the derivative finds the slope of a line at a given point. So if we were at this point, for example, we would see that we're increasing. At this point, the instantaneous rate of change, the slope at this point, is still going up. Here it's also going up. But there's going to be one point where we stop increasing, and then there's going to be another point where we're going down, going down, going down. And so the slope at this point is negative, negative, negative. Here it's positive, positive, positive. But there's going to be one point where we transition from positive slope to a negative slope. And that's going to be this point right here, for example. This is our stationary point. And that's where the slope would be equal to 0. Or we could say f prime of, actually, let's use it. Yeah, I'm going to use a few different notations. F prime of x is equal to 0, or in this case, where dA dx is equal to 0. That is to say, change in a over change in x is equal to 0. The slope is equal to 0 here. So, if we know dA dx is equal to 0 when we've reached a maximum, then let's substitute 0 in for dA dx. 0 is equal to 10 minus pi x over 2, and then we need to solve for x. Remember, pi isn't an unknown or anything like that, it's just a number. It's a special number, but it's just a number. So let's go into the calculator. We can solve this with algebra. Maybe I'll do that right now, because I think it's actually, I always think, I don't know, I think it's nice to. 20 over pi is equal to x. Did they ask us for an exact value? So sorry, I multiplied this by 2 and then divided by pi. If they're asking us for an exact value, that's what we need. Oh wow, they are, jeez. Oh my goodness. Okay, so they are actually expecting some rearranging of values. If we put this into the calculator, it's going to give us a decimal. So they're actually asking for rearranging of values. So let's take some more time and unpack this. Okay, so here is our equation. This 0 is equal to 10 minus pi x squared. Okay, I'm going to add pi x over 2 to both sides. Pi x over 2 to both sides. Remember, add something to both sides, keep everything balanced. If you're comfortable, you can also say, hey, let's just bring this over. If that is the way you've learned it, then that is also fine. Pi x over 2 is equal to 10. Alright. So essentially we want to get x all by itself. Next step, what do we want to do? Let's multiply this side by 2, multiply this side by 2, because our pi x is being divided by 2, and we want to get pi x by itself. These 2's are going to cancel out, and we're going to be left with pi x is equal to 20. We don't want pi x, we just want x all by itself. So let's divide out that pi. Remember, we can do the same thing to both sides. There we go. X is equal to 20 over pi. And I don't believe we are going to be able to solve this and find the exact value with the calculator. We can convert to decimal, approximate to fraction, but I don't believe that is going to work. I'm actually just going to try really quick by putting in the answer 20 over pi. If we get this and then we ask, for example, the calculator to approximate to a fraction, will it? No, it won't. And to be honest, looking at this value, I'm not sure if there's anything that 3.14 that says, hey, this is, divisible by pi. So I think actually they are asking for some algebraic manipulation. So in this case, even if we do graph it and find the maximum, it looks like we're going to need the exact value. So in this case, yeah, gotta know algebra. Got to know, or we have to know, how to work through this algebraic manipulation. And here it is. Here it is in the end. This x is equal to 20 over pi. All right. I hope that was helpful, and I think that finishes up with this exam. All right, everybody. Best of luck, and take care. Bye-bye.